Hello, curious minds. Have you ever dipped a pencil into a glass of water and noticed how it suddenly looks bent or broken? That simple everyday wonder actually gives us a sneak peek into a fascinating natural phenomenon called atmospheric refraction. So, what exactly is atmospheric refraction? It's the bending of light rays as they travel through the Earth's atmosphere caused by changes in air density. You see, air isn't the same everywhere. Temperature and pressure vary in different layers, making some parts denser than others. Now, imagine light from distant stars or the sun journeying through space and then entering our atmosphere. As it moves from the vacuum of space into the denser layers closer to Earth's surface, its speed slows down and it bends toward what we call the normal, an imaginary line perpendicular to the surface separating two layers. This bending makes stars and celestial objects appear in slightly shifted positions than where they truly are. Interestingly, the refractive index, that is, how much light bends, increases as you get closer to Earth's surface where the air is thickest. But atmospheric refraction isn't just for stargazing. It shapes many everyday sights such as the strangely squished or distorted look of sunsets and even mystical mirages on hot deserts. Isn't it amazing that the invisible layers of air all around us can bend light and play tricks on our eyes? Have you ever stared up at the night sky and wondered why stars seem to twinkle, flickering like tiny candles, while planets glow with a steady, calm light? This sparkling dance of stars, called stellar scintillation, is yet another enchanting result of atmospheric refraction. When the light from a distant star travels toward Earth, it must pass through countless layers of our atmosphere. Each layer is a mix of shifting temperatures and pressures, making the air unstable and turbulent. As starlight passes through these ever-changing layers, it bends unpredictably, causing the star's position to appear to wiggle and the light intensity to flicker when it finally reaches our eyes. Now, planets behave differently because, unlike stars which are point sources of light, planets appear as tiny disks. This means the fluctuating bending of light averages out over the planet's broader light surface, making their glow seem steadier. And guess what? The twinkling effect becomes even more dramatic when stars are near the horizon because their light travels through a much longer stretch of dense, turbulent atmosphere. So every twinkle you see is a beautiful reminder of the restless air layers wrapping around our planet. Let me share a curious sight you might have noticed. Sometimes the sun seems to peak above the horizon before it actually rises, or lingers a little longer after it has set. This wonder is all thanks to atmospheric refraction bending the sunlight in special ways. As the sunlight approaches Earth's atmosphere during sunrise or sunset, it passes through thick layers of colder, denser air near the surface. This bending, or refraction, causes the sun's rays to curve, making the sun appear slightly higher in the sky than its true geometric position. Because of this optical trick, our day feels about 2 minutes longer, a precious gift of extra daylight. Picture the path of sunlight bending like a gentle curve, allowing our eyes to see the sun even when it has slipped just below the horizon line. This fascinating distortion is a beautiful example of how our atmosphere shapes the rhythm of day and night, adding subtle magic to the rising and setting of our closest star. Imagine walking across a scorching desert or a hot asphalt road on a sunny day and suddenly seeing what looks like shimmering pools of water ahead. But as you move closer, the water disappears. This optical illusion is called a mirage, and it's a stunning example of atmospheric refraction at work. When the ground heats up intensely, the air just above it warms too, creating layers of progressively hotter, lighter air beneath cooler, denser air, a temperature gradient that affects air density. Because light bends toward denser air, these rays bend upward through the warm layers. So, Light coming from the blue sky gets bent and reaches your eyes at an angle that tricks your brain into perceiving it as a reflection, similar to how light reflects off water. In reality, no actual water is present. It's all about the curved path the light takes through the layers of air. This bending causes the image to appear inverted and shimmering on the surface ahead. Through this fascinating refractive dance of light, deserts and hot roads play delightful tricks on our vision, reminding us how nature's physics can create beautiful illusions. Let's take a closer look at how atmospheric refraction actually happens, step by step. As a beam of light travels from one atmospheric layer to another, each with a different air density, it bends according to Snell's law, a fundamental rule describing how light changes direction when passing between media of varying density. Since the air grows denser closer to Earth's surface, the refractive index progressively increases. This causes the light rays to bend steadily toward the normal, or the imaginary perpendicular line at the boundary of each layer. Instead of bending sharply at one point, the light curves smoothly, bending a little bit in many tiny steps across multiple layers. This cumulative bending makes celestial objects, like stars or the sun, appear higher in the sky than where they truly are. Interestingly, when light comes straight down vertically, there is no sideways bending, so atmospheric refraction is minimal or absent. But at shallow angles, like during sunrise or sunset, this effect becomes strong and creates the shifting sky we observe daily. Isn't it captivating how the atmosphere acts like a giant, invisible prism, continuously bending light in layers? Let's bring refraction right into our classroom with a simple yet revealing experiment. Take an empty glass beaker and place a coin at the bottom. Step back until the coin just disappears from your view. Now, pour water into the beaker and suddenly, the coin reappears. What's happening here? This is a live demonstration of how light bends or refracts when it moves from one medium to another. When the beaker is empty, light from the coin travels in a straight line but is blocked from your eyes at certain angles. When water is added, light bends as it passes from water to air, changing its path so that you can see the coin again. This bending of light shifts the apparent position of the coin, just like atmospheric refraction shifts the apparent position of stars and the sunday. This simple activity beautifully models the same principles that cause stars to twinkle, the sun to rise early, and desert mirages to appear. Through this hands-on experience, the mysterious bending of light feels closer to home, revealing the physics behind many natural spectacles. What an incredible journey we've taken exploring atmospheric refraction. From the sparkle of twinkling stars to the stretched moments of sunrise and sunset, and the shimmering mirages dancing on hot deserts, we've uncovered how light bends through invisible layers of air all around us. This bending happens because air density changes gradually with altitude, creating smooth curves in light's path rather than sudden leaps. We even tried a simple water and coin experiment to visualize refraction for ourselves, connecting the physics with what we see in the sky and in everyday life. Appreciating atmospheric refraction helps us understand not just nature's beauty but is crucial in fields like astronomy, weather prediction, and even designing optical technologies. Remember, the air might seem invisible, but it is a magnificent force that shapes how we view the world beyond. I hope this lesson opened your eyes to the subtle magic happening above you every moment. Biology, and science in general, is the study of life and its wondrous interactions, visible and invisible alike. Until next time, keep looking up and marveling at the endless secrets of our living, dynamic world.